Okay, I think we should go ahead and get started. We're a couple minutes past the start time, and people will continue to join us as we continue and get started. But I'll start out with introducing myself. I'm Lisa Stewart, the Chief Administrative Officer at the Kavli Institute for Theoretical Physics. It is my honor to welcome you for today's talk by Professor Phillips for the National Society of Black Physicists Innovate Seminar Series. Professor Phillips is a well-known and highly esteemed scientist here at KITP with over a half dozen talks in our online talks archive. And for many years, he served as an advisory board member here. That's all my way of saying that we are especially thrilled to host Dr. Phillips as today's speaker for this NSBP seminar series. Today's talk will be approximately 35 minutes and will be presented in webinar format. All questions will be held until the end. Please enter your questions into the Q&A section and following the talk, our speaker will try to address them as time permits. Next up, I'd like to introduce you to Farah Simpson, the student representative on NSBP's board and also the leader of the NSBP Student Council, which is the group responsible for creating and leading this Innovate Seminar Series. Thank you.
Hello, everyone. On behalf of the Student Council of the National Society of Black Physicists, I'd like to welcome you all back to the NSBP Innovate Seminar Series, where our members share the interesting and groundbreaking research that they're involved in. With that, I'd like to introduce the President of the National Society of Black Physicists, Dr. Stefan Alexander.
Hi, everyone. This is Stefan, and it's a great pleasure, in fact, a truly great pleasure to introduce my friend and colleague, Phillips. Well, I've known Philip, I don't know, maybe the last 30 years or so. And I can say that every time we hang out, I end up walking out a little bit smarter than I was before, because I end up learning some new physics. And I'm actually especially excited about this talk. There's a reason why we wanted him to speak today, because I suspect that we are in for a really big treat. Something I think that could be very important in physics. But I'll leave that up to you, the audience, to judge. Philip, started off, let's see, I'm going on memory here. So Philip, you could you can fact check me. Let's see, you did your PhD at the University of Washington in Seattle. Then you were a Miller Fellow, a prestigious Miller Fellow at UC Berkeley. And then from Berkeley, you went on to be a faculty at MIT for a couple of years. And then you were poached away by University of Illinois Urbana-Champaign, where I was able to, when I gave a colloquium there many years ago, bow in front of the statue of the great Jim Bardeen, who was that's right, one of the architects of the BCS theory of superconductivity. And today you're going to tell us something about that whole legacy and your contribution to date. One thing that y'all should know about Philip, though, that is that he's actually a very serious opera singer, and we'll just, maybe one day he'll bless us with some opera, because as you all know, I wrote a book all about the connections between music and physics. So maybe one day Philip will write a book about opera and physics. Philip, it's all yours. Thanks for being here.
Those of you who are waiting for that book, I suspect you'll be waiting a long time. Hey, thank you very much for this invitation. It's a pleasure. I'll be talking about one of my favorite topics, Mottness and superconductivity. And the words exact are now going to be linked. I never thought I would be giving a talk entitled with exact linking superconductivity and Mottness, but we have written a paper. It just came out in Nature Physics and there's a news and views on it by Jan Zanen. You can read all about it. This work was done with a student of mine, Luke Yeo, and Edwin Huang. He's a postdoc, and although he's a postdoc, he's actually younger than the student who is also very young. He's just very precocious. Okay, so I'm going to tell you about Mottness and superconductivity, why you should care about this. But first, let's just focus, I'll give you a 1-minute review of superconductivity. So superconductivity was discovered in 1911, and its key feature, one of the key features is the drop of the resistance to zero, here at 4.2 Kelvin, and this is in mercury, and discovered in 1911, Nobel Prize in 1913. The first hint as to how you might construct a microscopic theory was pointed out by Leon Cooper at Stefan's institution. And what he pointed out is that 2 electrons outside a Fermi surface, this is just the locus of points demarcating filled from empty states, and you turn this interaction on, this creates a pair of electrons in these particular momentum states. These electrons don't like to stay outside the Fermi surface. In fact, what they like to do is condense into an energy that's smaller than this, than outside. Hence, they lower their energy. But remember, everything here is filled. So what this is really telling you is that a Fermi surface is unstable to an attraction between 2 electrons just outside it. So what this might be telling you is that, in fact, the whole Fermi surface might, in fact, go away. A new state of matter might arise in which the basic gauge symmetry basic charge gauge symmetry is broken, and you get a condensate with a well-defined magnitude and a phase. There's a fundamental relationship between this theory of a Fermi surface and BCS superconductivity. And it's that fundamental relationship that allows us to say that superconductivity in metals is solved. If you start with a Fermi liquid, a bunch of non-interacting levels, there's a locus of points defining the dispersion for the highest occupied state, and that's indicated right here. That serves as an organizing principle. The moment you posit, you have a Fermi surface, and you add on repulsive interactions, you might generate some new states, but everything over here in the interacting system stands in a one-to-one correspondence with the states in the non-interacting system. And as a result of this one-to-one correspondence, which is the key tenet of Landau free liquid theory, what this suffices to guarantee is that the repulsive interactions are irrelevant. The only interaction which can destroy a Fermi surface is an attractive interaction with electrons on opposite sides of the Fermi surface. And that induces the BCS instability, and the classic equation that comes out of the paper of Bardeen, Cooper, and Schrieffer is 2 delta over KTC is 3.5. This is a number I want you to remember because we can compute that in our new theory. Okay, so this is well known, and because of the relevance of these repulsions, this is the only relevant interaction, superconductivity in metals is viewed as a solved problem because we've isolated all interactions. We can ignore everything except this one. So is there physics beyond BCS? This question, to my mind, is equivalent to asking, is there a new fixed point other than Fermi liquid theory? If Fermi liquid theory gives rise to BCS, it would stand to reason that some other normal state theory should give rise to some other kind of superconductivity. We have reason to believe that something like that is lurking out there, because I think it's safe to say the biggest problem in condensed matter physics is superconductivity in the cuprates. They start off their lives as Mott insulators, and they acquired this name because Mott, a very long time ago, was trying to understand why nickel oxide insulated. And the basic problem he faced is that it's D8. You put 10 electrons in a d orbital, which means there are lots of empty spaces for the electrons to hop. if there are empty spaces for the electrons to hop, the system should be a metal. But in fact, nickel oxide is a very good insulator. So what Mott thought about was, perhaps it costs a certain amount of energy when you move electrons from one orbital to the other. In fact, what he said, perhaps when this energy it costs to put 2 electrons here is bigger than the hopping matrix element, perhaps that opens a gap, and this gap is the origin of the insulating behavior. Now, the key point that Mott was trying to make, in addition to the gap, is that the system does this without changing the size of the Brillouin zone. I'll say exactly what I mean by that in a few minutes. So from Mott, we have local real space physics is causing this band picture of just counting up the empty spaces and saying the thing is if they're empty spaces, it's a metal. It's causing that simple-minded picture to break down. The basic model that comes into play here is the Hubbard model, which I'm not going to write down, but it basically has all those ingredients that Mott theorized about. A repulsion, when you put things on the same site and things can hop around. So if one says that high TC solved and the basic model is the Hubbard model, you have to show analytically how the Cooper instability comes about from the Hubbard model. The problem is you can only solve the Hubbard model in 1 dimension. And so anything like this is impossible in 2 dimensions where the cuprates really live. So what has been the progress that, thus far? Well, there are many acronyms that correspond to the various numerical approaches. I won't say what they are, but there are some. I've done some of these calculations, and that's where I learned about Mottness. But any problem this big and so intractable, there have to have been disputes. And a dispute which influenced my thinking about this profoundly was this dispute between 2 of the towering intellects of our field, Bob Laughlin and Phil Anderson. So what struck me is that these people are incredibly smart, but they have completely opposite views. So I decided to take this dispute seriously. And Bob is not holding any punches when he says that nowhere can one find any sort of clear exposition of what is meant by any of the terminology in the Mott problem. And since one can't, one should just forget about it, basically assume that Mott didn't know what he was talking about, and just go with symmetry broken states. Phil Anderson responded by saying that the first line of this paper is 10 years of some of the best minds that failed to produce anything like what is meant by the insulating state. And Phil is right about this. It is a tragedy of Mott that although he most certainly won his Nobel Prize for the Mott insulator, Slater, who couldn't think clearly about finite temperature, won the publicity battle. And what he means by that is the following. So here is Laughlin's objection. Laughlin's objection is that without breaking any symmetry, how can you possibly start from a non-interacting system, turn on some interaction, and if you follow all the arguments presented in 3 slides ago, there's no repulsion that you can add that you can show is relevant using Polchinski's arguments to a Fermi surface. How are you going to show in any sort of clear demonstrative way that you can form a gap? Now, the key thing here is that this gap isn't changing the size of the Brillouin zone. So the same momentum states that are here are also here. So what you have here is a splintering of each momentum state into something which has some component at high energies, some component at low energies. So you've broken the basic tenet of Fermi liquid theory, this 1-to-1 correspondence. It's 1 to 2, which is sufficient to break it. Okay, now if you can't demonstrate this, people are just going to be arguing about even the most basic concept in ITC, which they have. So it's because of this argument, I decided to ask the question, what is really the difference between what Bob Laughlin is saying and what Phil Anderson is saying? There has to be clearly something you can quantify, and it's that I set out to sort of figure out as my angle into this problem. The difference is what Mott had in his head, and that's what I call Mottness. And the difference between them is quantifiable. A certain quantity is zero. The quantity which is zero, I will tell you about very shortly, is this quantity. It's the real part of the green function. If it's more complicated, if they take the determinant of it, the determinant of this quantity is zero under what is called Mottness. And for symmetry broken states, it's not equal to zero. Okay, so let me introduce how you might want to think about this thing which is zero. Let's start off with a very simple thing. Let's just count particles. And counting particles is a very simple thing. It's one of the first things we learn to do. We count marbles, and let's just count them. 1, 2, and you can just go and do this procedure. So you can just see them and count them. We can't really count electrons this way. So is there a more efficient way? So I'm going to introduce the Luttinger counting theorem, and I'm going to simplify how you might think about this theorem. So consider this function, 1 over e minus epsilon p. E is the argument of this function, that is the probe energy. And let's look at what happens anytime E equals epsilon p. Epsilon p is the energy of a particle in a particular momentum state. Clearly, if E equals epsilon p, this thing blows up. So it might be that looking at some property of this might tell us something. So let's look at this function in the vicinity of this point. Well, when E is less than epsilon p, this thing's entirely negative. When E's bigger than epsilon p, it changes sign, becomes positive. So one way that you might count the number of particles is just use this as the probe and just count the number of sign changes you have. If you do that, you should be counting poles, which are quasi-particles, and hence you can formulate a very simple function that just counts the number of times a function changes sign. And that's just indicator here. You have two spins. Theta is the Heaviside step function. This function is only non-zero anytime the argument here is in fact positive. So you're counting the locus of points in momentum space where this function is positive. So this is a very clear statement. The problem and subtlety is this Heaviside step function doesn't care how the function became positive. And all of us learned a simpler way that a function can become positive without going through a pole. It can become positive by just going from negative to positive. And this thing counts these sorts of things as well. Now, the thing of it is, this function can never be zero. So if in fact you have a zero crossing, it's telling you that the green function, this quantity, the green function, looks completely different than something that's just counting that has pole-like quasi-particle excitations. Okay, and the more technical definition is the determinant of this is equal to zero. Okay, so zeros are telling you, so if in fact you get a zero, it's telling you there's no pole-like singularity. There's something that's causing the denominator to blow up, and that's giving rise to a breakdown of the particle concept. Okay, and that in fact is Mottness. Okay, so where's Mottness then? We start with a Fermi surface, we add repulsions. There's nothing that we technically can add to break this. So what went wrong? How do we think about this thing which should be there? So let's do something very radical. Let's think about a Mott insulator in momentum space, which is quite anathema to what Mott originally proposed and what everyone basically thinks. But that was exactly what was done in 1992 with the Hatsugai-Khomoto model. The first term is just the hopping term that's in the Hubbard model. But then the next term is very different than what you'd have in the Hubbard model. It looks like this, in which there's a long range interaction. It's an all-to-all interaction, but it's only all-to-all if the center of mass of these guys is the same as these guys. And this L to the D is put here to guarantee that this term is extensive. And I think they must have come up with this model by using reverse engineering, because if you just take the Fourier transform, and if you can do Fourier transforms in your head, you know exactly what is going to come about. Something very simple. It just looks like this. It looks like the single site version of the Hubbard model, but in momentum space. And if that problem is solvable, this problem is equally solvable. But the thing that's interesting is this. This produces the Fermi surface. This term right here, which was not considered in the original Polchinski type Shankar RG, this is a relevant interaction. Scale is s to the -2. So it has to give rise to new physics. So in fact, what you can show is that it gives rise to a Mott insulator. And here's the proof that it does. Anytime you have Mott physics, you have a splintering of each excitation into two different components. The things which completely diagonalize this problem are operators in momentum space, which are just the standard analogs of the operators that you have for the real space Hubbard model. So this is looking at a site in which which is empty. This one has already a particle on it. Okay, so if we have these, we can go and construct the green function exactly. Here is the solution to the green function. And notice, it doesn't look like 1 over some number. It looks like 1 over some number plus some other stuff. And it's this other stuff which is getting rid of the particle. This thing, you might call it the self-energy, though strictly speaking, it's not, because it has a pole in it. In other words, this is not perturbatively related to the non-interacting starting point. And that interaction is relevant is coming about here because the self-energy vanishes if you set that thing equal to 0. Okay, so here's the self-energy. This thing diverges anytime omega is equal to this. And it's both the real and the imaginary parts, which means the width of the state has gone off to infinity, and which means there is nothing like a Fermi liquid surviving. And in fact, there's a Mott transition. Here it is. Here are the two bands. And these are singly occupied, and here is the surface, the locus of points over which the determinant of the real part of the green function is equal to 0. And this is symmetrically located between these bands. One can move these around by doping the system, et cetera, but there is a surface of zeros. And that's guaranteed by the fact that you have spectral weight here and spectral weight here. So the answer to Lofton's question is yes, there is a well-defined model you can construct, and it was constructed in 1992. Lofton just didn't do his homework, and it shows you exactly how to think about lower and upper Hubbard bands. Now, when U is less than W, the bands cross the chemical potential. There is this surface is only there for the singly occupied part, and here's now the singly occupied part. Here are the numbers for the yes. this is completely filled, this range of momenta, this is singly occupied, and this is empty. If this would be a Fermi liquid if you didn't have the singly occupied part, but everything would be very simple. Because you have this repulsion between the K states, this is why you're getting spectral weight at high and low energies, and this surface of zeros separating them. So if you look at the system, it has all of the ingredients to now just to formulate, to count the number of particles. And it should be a fairly simple counting procedure. But remember now, so here, yes, this is what this looks like for U bigger than W and less than 1. Just this band crosses the chemical potential, and the surface of zeros now is here. And here's the exact solution to this model under very generic circumstances. If the occupancy here is supposed to be 1, and it's not, which means in general, this is a non-Fermi liquid. And we can do every calculation completely exactly. And hence we can ask the question, is there any kind of superconducting instability? We have complete control of a normal state, which is not a Fermi liquid. Let's see how far we can get in pursuit of superconductivity in this Mott insulating or dope Mott insulating state. Now, this model leaves something out, and that's why it's solvable. Unlike the Hubbard model, in which it's impossible to separate the Mott gap from this sort of dynamical spectral wave transfer, namely that if you start off with a fixed number of empty sites and you run the system, you end up with more than those. I have 3 empty sites, I start out with 1, and that's because I now have this double occupancy. So this is an inherent feature of the Hubbard model, and this comes about from the non-commutativity of these 2 terms in the Hamiltonian. In our case, we have 2 terms that commute, and that's why the system is solvable. When you turn on the interaction, though, the eigenstates change completely, but it is the thing that allows you to solve the problem. So this is known as dynamical spectral wave transfer. It's a higher order correction. It is not there, but the bifurcation of the bands into 2 upper and lower things is certainly there in the Hatsugai-Khomoto model. Okay, now the thing I realized last summer is that because of this feature, you can formulate the Cooper instability exactly. You just add on the standard term that Cooper added, and the question you're asking here is there an analog of this instability for a Fermi surface or a Luttinger surface? And we have an exact theory for Luttinger surface, so we can just go and calculate it. Here's this pair term. This is the wave function. You're only summing over the part that's unoccupied. In fact, you can generalize and do this for any possible state. The binding energy you compute should be the difference between the ground state in the absence of this term and the ground state in the presence of this term. And the question you're asking is this term dominating? Is the binding energy negative? You can formulate this problem exactly. Here it is. Set these equal to 0. This is it right here. And here you are. Here's the Cooper instability in a dope Mott insulator. And this is a limiting form of this expression. And yeah, there is a Cooper instability. So what this suggests then is that the ground state is superconducting. The nice thing about this model is that even with this pair term, you can go and calculate the pair susceptibility completely exactly. This is the quantity you have to go and calculate, and it's because of the form of the Hamiltonian. And it factorizes in this form. This is determined by this. When this denominator is equal to 0, that determines the critical temperature. You can solve for Tc, and here is a limiting form of Tc when the interaction strength is less than U. Okay, so we have a superconducting state. induced by this pair interaction. Now, what made BCS what it is that you can compute everything with it. And the workhorse of that was the wave function. So what BCS said is that we can write down a variational wave function for our pair Hamiltonian, and these are the variational parameters. And the reason why this works is that with only two parameters, you can model exactly the wave function for the non-interacting system, the Fermi liquid. This is just an operator which creates a pair. Now, how many operators? So before I get to that, let me just note the following. This is just some simple algebra. You can rewrite this BCS wave function by only taking a product over the positive momentum states by just writing it like this. Now, the reason I did this is exactly what we need to model our system, because there's a doubly occupied part, there's a singly occupied part, and an empty part. In the Fermi liquid, there's no singly occupied part because there's no repulsion in momentum space. So here it is. What we do is we generalize the BCS wave function to something that allows us to have three independent variational parameters. This corresponds to the doubly occupied sector. This is the empty part of the spectrum, indicated right here. This and this is doubly occupied. And then this part right here is the singly occupied part. This is the Mott physics. And it's on both, it has a compound both at low and high energies. And that is crucial in determining what are the excitations from this weird superconducting state. Okay, so there are a lot of technical details here. You have three variational parameters. You just go and compute the ground state energy. You can get the gap out, and the gap looks like this. This is in this limiting form. And the key thing about this gap is we can now take the ratio of the gap to TC. Notice there are very different exponents here, which means in the limit that G goes to 0, which is the sort of, you're assuming you're perturbatively close to the unpaired state. This ratio should go to 3.5 in BCS. And that's because the exponent here and here are identical. It's not the case here. This ratio is infinity. So this is very much unlike BCS superconductivity. Now we can do more than that. Because we have a wave function, in fact, we can go and calculate everything BCS did. And we're in the process of increasing the range of things that we can go and calculate. Okay, one of the things that we can do is we can ask the question, what are the basic excitations? Now, the excitations are finite temperature excitations. There are none of those in the BCS wave function. Everything's in the ground state, which means that if there is such an excitation out of the BCS state, acting on the BCS state with that operator should kill it. Now, in BCS, these elementary excitations are linear combinations of just the basic electrons, just a hole and a particle with some coherence vectors. That's not the case here. These new excitations we have dubbed pions after our initials in the paper, Phillips, Yeo, Huang. And these are not Bogolubov excitations. These excitations, coming from the fact that you have Mottness, are now made out of holes and particle combinations of these Hubbard composite operators. And so, you can easily formulate them. And we know this is true because you operate this on this wave function, you end up with 0. In fact, you can prove that these things are gapped from the ground state simply by going computing this. And this quantity right here is in fact the thing that has the excitation, the gap in it. So these things really are the new Bogolub, the new quasi-particle excitations. These are the pion excitations. They're replacing Bogolubov quasi-particles, and they are gapped. Okay, so what does, and there's a component in the upper band and the lower band, as it must be, because that's the odd part of the whole spectrum. So what you would get in BCS is just the opening of a gap in just the Fermi liquid band. But here, because you have components at high and low energies, you get, this is the pion band. And there's a component here, and there's one in the upper band as well. So it's a much more complicated, rich structure. And as a result of this component here at high energies, we have the ingredients to explain a long-standing experimental puzzle. The experimental puzzle is what has been dubbed the color change. And it's the fact that when high temperature superconductors, here this is just BISCO, when it superconducts, there's a change, there's an induced spectral wave transfer from high to low energies. So if you simply count the low energy part by this, integrate from 0 up to some cutoff, and the high energy part from that cutoff up to the top of the band, if there's a transfer, there should be a decrease in this and an increase in that. And that's what they saw experimentally. Okay, so this now is the low energy part. This thing is decreasing and this thing is increasing. Right when you see, right at TC, you have this accelerated increase of the spectral wave. Okay, and as far as I know, no one's been able to get this out in any sort of, microscopic theory. Now, the reason, and this change in the spectral weight relative to the original one is around 3%. Now, the reason why this is profound is that the experimentalists noticed that all this is a small quantity. It's large enough to explain the condensation energy. So here you have a low energy property that's influenced by the change in the spectral weight from the UV into the IR. So we can go and calculate this with this wave function, and here's the result. So we're looking at the total weight in the lower band relative to the weight when you didn't have superconductivity. Now this starts at 1. So this quantity is in fact positive. And the change here is roughly what you see, you look at some value of this coupling constant, it's right on the order of magnitude for what you see, for what is seen experimentally. Okay, now, the thing of it is this quantity is decreasing as you increase the ratio of U over T, which means it's tied to the fact that when you include the pair term, you've destroyed this commutativity. That is leading to dynamical spectral wave transfer, and hence you have this extra mixing between the bands. That is the general mechanism that we've come up with as the reason you have this color change. Okay, so the question we ask is this true in general? It's certainly true in the HK model. No one, as far as I know, has calculated this for the Hubbard model or any simulations which have revealed this. Okay, now the last thing we can compute is the superfluid density. So this is what the superfluid density looks like for a Fermi liquid. It has to be 0 at the ends because this is no particles. This is an insulator. There has to be a peak somewhere in the middle as you turn on the coupling to the attractive interaction. We can go and do this using our PHY or PYH wave function, and the answer is right here. And you know what the answer has to look like? It has to respect Mottness, so it has to be a sum of 2 domes. It has to be an insulator here. There's some peak somewhere in the middle. On either side of half filling, you get this dome-like structure. So right here, if you look at the value relative to this is a huge suppression of the spectral weight, of the superfluid density. And this is coming entirely because of the proximity to the Mott insulator, which is right here. Okay, so to summarize, what have we done? We've done something which probably we shouldn't have done. We asked the question, can you have a Mott insulator in momentum space? And as far as I can tell, there's no difference between this and putting it in real space. The only thing you're doing is, the only thing that's necessary is some penalty for occupying the same state. The real space problem is a lot more complicated to solve. This one is solvable exactly. And the general problem of HK is any interaction which looks like this. Using the standard arguments, this interaction is relevant. Any interaction of this form, it commutes, but it gives you a non-trivial metal insulator transition. It gives you a Mott gap. Non-BCS superconductivity. It can explain the color change, and it gives you these pion excitations. So one of the questions that arises is, we know what we've left out. Can we put all of that stuff back in and show that we can somehow retain what we have? So this is really to show that this really is a fixed point. You can ask me questions about that, but this is the message that is in this paper.
Excellent. Well, let's thank the speaker.
I can only hear you.
So the way it's going to work now is that we will call on some questions. So basically, I'm going to moderate the questions. Because of time, we'll only have time for a few questions and hopefully conversations depending on Phillips' response. So we'll begin with a question from the panel, from the participants, and then I'll open it up, and we'll unmute to have someone else ask a question, and then I will moderate after that. So let's begin with a question from, so Philip, do we have a question from Ivan or Ivan?
Ivan Bozler, yes, I see the question.
Okay.
Is there any justification for the HK model? As I said, Ivan, it's an excellent question. Look, it doesn't matter if you formulate the Mott problem in momentum space or real space. I think we have been tethered to real space, but I think what this shows is that that was not necessarily a wise thing to do.
Okay, I actually want to call on another dear colleague and mentor of mine, David Gross, to maybe throw a bone, a question or something like that to Philip, or a comment.
Oh, very interesting. But normally there's a reason we stick to real space. It's called locality. So how non-local are these interaction terms?
Right. Okay. Well, part of the reason why I resurrected this model is the popularity of SYK, which you have worked on. And I knew about this model, and it just occurred to me that no one had...
Explain to us what SYK is actually.
It's the Sachdev-Yi-Kitaev model, which, for those of us in condensed matter, we all knew about the Sachdev-Yi model, and that was replaced by the RSY model. And then this became famous because it has a gravity dual. Look, it's less non-local than your favorite SYK model. Okay? Right. So, I mean, if people are going to do SYK, I'm going to do HK.
But the SYK model is originally formulated, is a model in one dimension, in zeros.
Yeah, that's right. This is not so. This is valid in any spatial dimension. I would make the following analog. We know the Sherrington-Kirkpatrick model. It's a non-local model for spin glasses, solvable exactly. This is, I would say, but that's sort of a mean field. This is in the spirit of Sherrington-Kirkpatrick.
Well, the Sherrington-Kirkpatrick, as you say, is mean field. It's sort of infinite dimensional model, right? Where every spin.
Yeah, that's right. That's what I said. It's not really the same thing. Because of this hopping term, you can. This model is definable completely in any dimension you want and solvable at any dimension.
All I was asking really was, if I go back to real space and try to formulate this model in real space, corresponds to some kind of non-local.
Yeah, that's right. Oh, so maybe you missed that. Here it is. Let me play this again. Okay, so here it is.
Right.
Oh boy, I have to stop sharing and share again. Oh, here it is. Okay, now I need to start sharing again. Okay, and play. Yes. Here you go. So this is the interaction.
Right.
So it's between any pairs of sites that have this constraint.
I got it. But that in real space is
This is in real space.
very long range interaction.
Yeah. Look, it's absolutely.
So,
I mean,
right. So it's a fascinating model because it's so soluble. But what does it mean in real space? How can this mimic some dynamical effect that arises from local spin-spin interactions?
Okay, so the answer to that is it cannot. And I think that's where we've been that has been the bottleneck. And Mott physics has long wavelength properties and short range physics. And the Hubbard model is great at getting the short range physics right. If you're going to try to answer questions like superconductivity, I would say you're better suited by solving this model, because that's really the long distance physics.
Right, but wouldn't you have to justify that long distance physics from some microscopic model?
Okay, so I would justify it the following way. If I have this interaction, if you just use the same arguments in Polchinski's paper, this thing is relevant, which means it does destroy the Fermi surface. And in fact, it gives rise to a bifurcation of the bands into two. And so it has Mott physics in it.
Right, but you're starting, it sort of turned on its head, because normally you start and you say you have some theory, and then a relevant perturbation is one that becomes more and more important as you integrate out local degrees of freedom and look at the long distance behavior. Whereas here you're starting with something which is very long distant. So I'm not sure how I think about the renormalization group arguments in momentum space.
Well, on that very interesting note, I mean, this is exactly the point of the NSBP Kavli talks, is to exactly get these conversations to the point where maybe you and David write a paper on this.
David,
yeah.
I mean,
So in other words, let me say that there are other questions waiting in line here. So, I'll answer the question, and then we'll move on to two more questions. Actually, it's a great question, though. Philip?
Yeah. Yeah, okay, so David, I would say that I think we've been misguided. As a result of this, I don't see that you are impoverished by considering a momentum space analog of a Mott insulator. I think it's just a bias that we've had. I mean, as long as you put in this repulsion between the momentum states, you have all the physics that you really care about, except the dynamical spectral wave transfer. Now, the point of it is, it's easier to think about how you would construct one in real space, but I don't want to, the fact that I can't think of how I would do it in momentum space shouldn't be a reason why I shouldn't consider the model.
Okay,
I mean,
great. So we hope that continues on offline between you and David. I especially appreciate that renormalization group point. That's very interesting for other reasons. So we have another question from William Radcliffe, great NSBP member. I believe Bill is actually an experimentalist. And his question is, can you discuss magnetism in this context?
No.
Maybe we should redirect, huh?
Yeah,
in other words, yeah.
Good.
Mm-hmm.
There is no magnetism here. And I think, look, I'd say the earliest, the antiferromagnet is there, okay? It goes away. And there are a lot of people who have formulated theories far away from the antiferromagnet based on spin fluctuations. I think that's not the correct thing to do. I think that has served as a crutch to devise theories which I think are not well-founded. And this has no magnetism in it. Okay, I mean, that's not what it's designed to do. It's not designed to get short-range physics right.
Mm-hmm.
So what
it's
it really
kind of related to David's question.
So this is in the spirit of what Mott was trying to do. Mott wanted to divorce magnetism from the gap. The Hatsugai-Khomoto model does that exactly. So it doesn't mix up the two phenomena. If you write down the Hubbard model, it's all mixed together. Hatsugai-Khomoto, you just get the gap. So it has nothing to do with, ordering. It's just Mottness.
Okay, good. So the final question we'll ask is from Aravind Shankar. I hope I pronounced his first name correctly. His question is, for U less than W, and maybe you can define that in a second. Would you say that there's two Fermi surfaces? And how does that affect the Cooper pairing?
Okay, let me get to that. Here you are. Okay, that is the key, one of the key points. Okay, for U less than W, these in no way should these be construed as Fermi surfaces. You might think that, but Fermi surfaces don't have spectral weight here and here, and they aren't completely occupied. No Fermi surface looks like that. Plus, if you look at the green function, it has zeros in it. And this is the line of zeros here. It's entirely covering the region here where this is singly occupied. Okay? Which means that if this system becomes superconducting, it's really coming about from excitations here and here. And that's what these pion excitations are. They are linear combinations of particles and holes living at low and high energies. And that is what I showed right here. Yes. These are the pion bands. Okay, so superconductivity is causing a gap both in the upper band and in the lower band. Okay, and that is giving rise to the color change that is seen experimentally, which, as far as I know, no one has been able to explain.
Okay, so then I'll end with a question from me. So as you know, we in the high energy world, there's always been an interplay between findings in condensed matter, theoretical constructs in condensed matter systems, and for example, in particle physics, where I live sometimes in cosmology nowadays. And we've definitely used the Cooper pairing mechanism in ordinary metallic superconductors to talk about things like pions, which is, Nambu's realization of Cooper pairs, or the initial instantiation of even the Higgs mechanism, in the realm now of compositeness, for something that might look like the Higgs particle. So would you imagine in a far future, if you're correct, that we will have further analogs in high energy physics of this mechanism? What would that look like?
Yeah, okay, so look, I think okay, so I know people are sort of shocked by this model, but they shouldn't be. It's been around since 1992, but everyone ignored it. But look at the SYK model. That's a non-local model. That's having impact in both condensed matter and high energy. I think the fact that high TCs remain unsolved until continues to remain unsolved, and the only solvable model that gives you any inkling of what it looks like is this model, tells you that perhaps non-locality is something we should take more seriously. And certainly a large part of my effort has been on trying to understand how you could construct non-local theories, what this means for the gauge structure, what do the OPEs look like? Because I don't think the answer to high TC involves anything local. I think it's entirely non-local physics.
Okay.
So, which is why I like SYK, but people have done that. Okay, it's time to do something else.
Right. Well, on that note, Philip, on behalf of NSBP and of course our hosts, the KITP, it's been great having you. And of course, this will be posted and edited down, and we look forward to sharing it across the spectral index. And on that note, wish everybody a great rest of the week, and see you at the next NSBP Innovate Seminar Series.